Today's topic is titration, another classic example of a chemistry problem that you not only encounter on exams, but also usually something you perform in a general chemistry lab. So we're going to look at the case of a strong acid, strong base titration, and we're going to learn how to understand the setup and solve a couple examples of titration problems. First, we want to visit or revisit titration principles. The basic principle of a titration is we can use a solution of known concentration to titrate, fancy word for react with, a second solution of unknown concentration. So imagine in this burette here, you have a solution of known concentration. You let it go drop by drop into a solution of another chemical species, usually known as the analyte, and this is of unknown concentration. What is the goal? The goal is to find the concentration of the unknown from the information you have using a solution of known concentration and of a certain volume. So in this example, as noted, we're going to, for example, titrate an acid chemical species of unknown concentration with a base chemical species of known concentration, and we're going to use the data that we collect in order to ascertain the concentration of the unknown. Here is a typical acid-base titration. NaOH, a strong base, is reacted with HCl, and when these two, when this base reacts with this acid, we get what is known as a salt, an ionic compound, and water. One thing that's important to take note of here is that the base will react with the acid, or the other way around, until they have actually completely consumed one another. You can actually think of them as eating each other up. And in the process of eating each other up, they make these new compounds, salt and water. So what happens if you react exactly equal quantities of NaOH and HCl? Well, naturally, they consume one another completely, and then you have reached something called the neutralization point. Why neutralization? Well, it just so happens that NaCl and water have a neutral pH, hence this term. But you're also going to see the terms endpoint and equivalence point. These all mean the same thing. Neutralization is endpoint, is equivalence point. The main thing you have to understand is that the acid and the base have completely reacted with one another, and there's none of either one left. If you continue with your titration after all the acid has consumed all the base, or vice versa, then if you add more, let's say we are titrating an acid of unknown concentration with a base of known concentration. Once you've added just enough base in this apparatus to consume all the acid down here, once all the acid is gone, if you add just another drop of NaOH, keep in mind there's no more acid for it to react with. So it has essentially nothing to react with, except, cleverly, we have added something to this unknown concentration solution here that is called an indicator. That means if you put in that extra drop of NaOH, even one drop, instead of reacting with the acid, which is now all gone, it's going to react with the indicator, which is why you have the change in color. that just tiny amount of excess base is now reacting with indicator, usually something unpronounceable. I'm going to call it phenol whatchamacallit, but it does have a real name. In any event, the main point is your solution changes color, and that's the indication that you have reached that neutralization /end/equivalence point. To go through all the steps before we solve a problem, imagine you have put in a beaker a certain volume of acid solution of unknown concentration. You add a drop or two of indicator. Then you start titrating with your base of known concentration. The burette gives you a very precise way to read volume. So you take an initial reading and you take a final reading when you hit that equivalence neutralization point we just spoke about, where you have the color change. And you can get the volume dispensed of your solution of known concentration by simply measuring the distance or subtracting to find the difference in order to get the volume that you have actually let drip into your beaker here. Okay, so think about this for a moment. If you know the volume that you have dispensed and you know the concentration of what's in the burette, you have a way to calculate moles. Why? M equals N over V, N being moles. So you can simply rearrange that equation to find how many moles of titrant you have dispensed into your flask. And that's going to be the key to solving your titration problem. Here we have two problems. The first one is fairly simple, and the second one is just a little bit more challenging. The difference between these two is in this first problem, we have a 1-to-1 mole ratio between HCl and NaOH. And in the second one, we're going to see when we write the balanced equation that we don't have a 1-to-1 ratio between calcium hydroxide and phosphoric acid. So this is the only difference between these two problems, but we're going to go through them. I'm not going to read them right now or anything. We're going to go through them one at a time. Okay, so here's the first one. We take 20.6 ml of 0.1 molar aqueous HCl. We use it to titrate 30 ml of a solution of NaOH. NaOH is of unknown concentration. It takes 20.6 ml of our 0.01 molar HCl in order to get to the equivalence point. So now we're using this to find the molarity of the NaOH solution. So what are our weapons? Our weapons are the balanced equation and M equals N over V. This is crucial to have this equation at your disposal and to be able to rearrange it to solve for moles. So let's do that. We can use the volume and the molarity of HCl to get moles of HCl. We're simply going to take this equation and say N equals molarity times volume. That is, note, we have to convert to liters, so we're going to take our 20.6 ml. We're going to move that decimal point back 3 places, and we're going to get 0.0206 liters times 0.01 moles per liter. Notice how liters cancel here, and we find that we have 0.0026 moles of HCl. Now notice in this balanced equation, it is a 1-to-1 ratio. So we can say that to get to the equivalence point, the moles of HCl equals the moles of NaOH. It took precisely 0.00026 moles of HCl to react with the same amount of NaOH, and we know that from the balanced equation. So now all we have to do to get the molarity of NaOH is to take this mole amount and divide it by 0.03 liters. Why 0.03? Because that is the volume of our NaOH. And the only thing that matters for molarity is the moles of NaOH divided by its own volume. Don't make the mistake of trying to combine volumes here. It is simply the volume of our NaOH. And we get a number. That turns out to be 6.867 times 10 to the negative third molar. You might be asking yourself, why do we even do this? Is this a pointless exercise? Or is there an actual reason behind it? Well, of course, I hope you believe there's a reason behind it. This is something called standardization. Sometimes if we think we create a solution of a certain molarity, it's not entirely accurate. So when we do a titration in a process called quantitative analysis, we then have a better and more precise idea of what the molarity of our solution actually really is. Let's go on to the next problem. Now we will take a look at what happens, or what the situation is, if we have a calcium hydroxide solution which has a volume of 12.5 milliliters. You have to read this one carefully, because this is our unknown and this is its volume, 12.5 ml of calcium hydroxide. In order to neutralize it, we titrated 10 ml of 0.6 molar phosphoric acid. The process is going to be similar to the last time, except the balanced equation is now not in a 1-to-1 molar ratio. We need 3 moles of calcium hydroxide for every 2 moles of phosphoric acid, or vice versa. We could say 2 to 3. We need, as usual, M equals N over V, but because of the stoichiometry here, we have to incorporate in our calculations the mole-to-mole ratio between calcium hydroxide and phosphoric acid. We're going to start from the same place. We're going to take our 10 ml and convert it to liters. We're going to multiply that by the molarity, N equals M times V, and we're going to find out that we have 0.006 moles of phosphoric acid that we had to add to our calcium hydroxide in order to get to the neutralization point. However, 0.006 mole of phosphoric acid does not react in a 1-to-1 ratio with calcium hydroxide. So we're going to have to say we need 3 moles of calcium hydroxide for every 2 moles of phosphoric acid. And that will tell us that actually there is 0.009 moles of calcium hydroxide in our unknown solution, unknown concentration. Now that we have 0.009 moles, we again do the same thing. We divide by the volume of the calcium hydroxide, which when we convert to liters is 0.0125 liters, and that gives us a molarity of 0.720. 2 different examples. Just focus on the first one being the 1-to-1 molar ratio and the second one being a non-1-to-1 molar ratio. Somewhere along the line, you may have been convinced to use the formula C1V1 equals C2V2. I do not recommend this for several reasons. One is you don't have as good an idea of what it is that's actually going on in terms of the whole process. And also, you can get messed up here with your stoichiometric coefficients. There is a way to incorporate them in this equation, but it's easy to make a mistake, so I don't recommend it. Okay, tons, as always, of titration problems online. Go forth and conquer.